Have you ever been caught in a rainstorm without a coat and thought, bother, I wish I could have seen this coming? Or maybe you've experienced an even bigger betrayal. You checked your weather app and it told you there's only a 10% chance of rain, so you risked it. And now you're drenched. Meteorologists use math to try to describe the world and predict the future. Same as biologists, economists, political pollsters, professional gamblers, almost anything else you might dream of being. Mathematicians call this modeling. But any model that's trying to capture a world filled with chaotic particles, not to mention humans who make irrational decisions and live complicated lives, will just look pretty messy. Instead of turning to a deck of tarot cards or crystal ball, to make things simpler, we can use polynomials. A polynomial is an algebraic quantity where the variables involved have only whole non-negative exponents, like in x squared or x to the fifth. And they can actually approximate a lot of messy models we might create to get some answers. So today we'll learn the basics of manipulating polynomials. Let's see what mathematicians use to tell the future. G'day, I'm James Tanton, and this is Study Hall Algebra presented by Arizona State University and Crash Course. Before we dive in, let's remember the difference between an algebraic expression and an algebraic equation. Algebraic expressions are generic quantities that combine numbers and variables. 5x plus 3 is a polynomial expression because it's just a quantity, and it's polynomial because the variables have only whole non-negative exponents. And here, x can be anything. But algebraic equations are trying to say something specific, that there is an equality between two quantities. For example, 5x plus 3 equals 13 is a polynomial equation with a single solution x equals 2. Now, we won't pretend you'll ever multiply or divide complicated expressions by hand after algebra class, but you will need to know how to tell a computer what to do and be able to interpret whatever it spits out. Adding and subtracting polynomials is basically just collecting like terms, or terms with the same variable raised to the same exponent. It's fiddly work, but straightforward if you have a system. A lot of the work comes down to paying attention to the coefficients, or the numbers multiplying our variables, like the 4 in 4x. But multiplying polynomials is more convoluted, especially for long expressions. The box method, which we first saw with negative numbers, is excellent for keeping careful track of how each term gets distributed, like for multiplying great big galumphing polynomials. If we have to multiply something like 3x squared plus 2x minus 7 by 4x squared plus 3x plus 5, well, I don't know about you, but if I try to do that in my head, I'd probably just fall down. But if we divide this up into boxes, nothing gets missed. For the first row, 3x squared times 4x squared is 12x to the fourth. 2x times 4x squared is 8x cubed. Negative 7 times 4x squared is negative 28x squared. Order doesn't matter as long as every box gets filled in. To finish, we can clean up by adding all the terms together, reordering them from highest power to lowest power, and collecting like terms. Multiplication is all about organization. But polynomial division is all about solving mysteries. We're actually working with two types of mysteries here. In one, we're given a polynomial and directly instructed to divide it by another. And in the other, we're factoring, or figuring out what polynomials multiply together to produce our original polynomial. Oh, somewhere in these math goggles, there's a magnifying glass setting that actually help us make these deductions. The product, 6x cubed plus 6x squared plus 3x minus 15. The criminal mastermind, 2x squared plus 4x plus 5. We just need our accomplice to complete the puzzle, and we're on the case. We'll start by lining everything up, just as it was at the scene. Unfortunately, some of our evidence is compromised. We know we've added or subtracted some terms together to get that 3x, for example, so let's not fill that one in just yet. But our first term and our last term are almost always safe to fill in because they don't come from combining like terms. Examining their coefficients might help us bust this case wide open. What could turn 2x squared into 6x cubed? Well, the coefficient must have been 3, since 2 times 3 is 6. And to turn x squared into x cubed, there must have been an x involved too. So odds are this first guy works under the name 3x. This term had its mitts all over the first row. 3x times 4x is 12x squared. 3x times 5 is 15x. As soon as we pin down one of these characters, we can round them all up. Let's put the screws to that negative 15. What could have come along and turned that innocent 5 into negative 15? A negative 3 must have done it. And when we pencil that in, suddenly we've got everybody. Negative 3 times 2x squared is negative 6x squared, and negative 3 times 4x is negative 12x. Now it's time to check that all these stories add up. 6x cubed, good. 12x squared minus 6x squared, that gives us 6x squared. Checks out so far. 15x minus 12x gives us 3x. And we can close the case. Factoring is also like working backwards from the scene of a crime. But this time we only have one polynomial to start with. Let's say we have something like x squared plus 2x minus 8. We want to split it up into two smaller polynomials. Two quantities were multiplied together here to produce an x squared. And our first guess is that it probably comes from x times x. But what about that negative 8? Guessing is harder here. It could be the product of negative 1 and 8, or 1 and negative 8, or 2 and negative 4, or negative 2 and 4. To decide, we can interview the coefficient of the 2x term. It suggests that the constants aren't so far apart as 1 and 8 suggest, because negative 8 plus 1x add up to negative 7x, or 8x minus 1x is 7x. So we want to pair with a small gap, like 2 and 4. The larger number is probably positive because 2 is positive, and a large number minus a small number will still be positive. So we'll guess that our factors are x plus 4 and x minus 2. Now we might have to try a couple of options, but that's absolutely fine. Every good mystery has a few red herrings. As long as we establish a list of suspected factors and we're patient, we'll get them all in the end. Now factoring might seem like complicated rewriting, but it reveals important secrets about whatever pattern we're trying to describe that the expanded polynomial just might be hiding. X squared plus 2x minus 8 wasn't giving up that x equals negative 4 and x equals 2 actually make the polynomial equal to 0. But the factored version was ready to spill the beans. So, after all the work we've done expanding number systems and exploring different rules, can we solve every type of equation out there? Figuring out when we're done with numbers is definitely, as mathematicians would say, non-trivial or not obvious. We know there must be something else out there when we come across something like x squared equals negative 9. Nothing that we have so far solves that equation. So, we need to use a number that doesn't actually exist in the real world. Mathematicians filled this gap by introducing the number I for imaginary. I know it doesn't look like a number, but we had to come up with something with a fanciful property that if you square it, you get negative 1. Sometimes we get backed into a corner by the simultaneous need to take the square root of a negative number and the fact that there is no such thing as the square root of a negative number. But I actually makes it all possible. Now take x squared equals negative 9. Actually, if this were x squared equals positive 9, we would say that there are two solutions, x equals 3 and x equals negative 3. But now we want something squared to be negative 9. Stick an I in and instead try x equals 3i and x equals negative 3i. 3i squared is 3 times I times 3 times I, which is 9 times I squared, which is 9 times negative 1, which is negative 9. Woohoo! And negative 3i squared is negative 3 times I times negative 3 times I, which is 9 times I squared again, which is negative 9. Double woohoo! One of the greatest surprises in the human story of mathematics is that the imaginary numbers are enough to solve all polynomial equations. We've needed more and more new ideas and techniques, negative numbers, rational expressions, irrational numbers, logarithms, as we come up against different types of equations. So we might begin to wonder if even more new, weird, fantastical numbers are needed to solve even more equations. But with imaginary numbers, mathematicians were able to prove the fundamental theorem of algebra, which guarantees that every polynomial equation can be solved with an integer, a fraction, an irrational, or an imaginary number. And knowing that all equations have solutions means we can go ahead and create algorithms or write programs for finding solutions to equations without fear of a program ever crashing. While these imaginary solutions might not have real-world meaning, they do make sure that all the math works. So, now we're polynomial masters, right? We can solve, multiply, and factor almost anything algebra throws at us. But it's always possible to get stuck, so here's some tips for you if you do. When adding and subtracting polynomials, it's important to stay organized. Stack your polynomials and align variables with the same power. Rectangles are still our friends. The box method works for both multiplication and division. Filling in the last and first terms of the dividend will help you sleuth out what your factors are. And if you need to take the square root of a negative number, there's an imaginary number lurking in there. Remember that you'll still get both a positive and a negative version of the root. Next time we'll go deeper into polynomials and look at one of the most famous, if not infamous types, the quadratic equation. So until then, cheers. Thanks for watching Study Hall Algebra, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video and want to keep learning with us here at Study Hall, be sure to subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.